everyone. Welcome to the Egyptian Society of Subsea Engineers. Today, we're hosting our guest speaker, Mr. Paul, and today, hopefully, they're gonna help us learn know about rapid pipe by cladtek. And I'm interested in myself to learn about this. It's my first time to hear about the solutions. So I hope we all learn something new today and they have a good time with us. Also, thank you, Mr. Paul, for your time. And we're looking forward to hear what you have to say. Okay.
Okay, well, so good morning, good afternoon, everyone, wherever you are. Thank you very much, Mr. Chairman. Thank you for this opportunity. My name is Paul Montague, and I'm joined by my colleague, Stephen Vorley. So I'm the founder of cladtek, and my role in cladtek is Director of Product and Business Development. So I'm going to give you a very short overview, just a little bit about cladtek, just a few short slides, then speak about connectors or the industry experience with connectors for flow lines and risers over the last 20 to 30 years, and then specifically about the rapid pipe connector, and my colleague Stephen will join and help out with the technical explanation of rapid pipe. So I'll just share my screen. So is everybody seeing my screen now?
Yeah.
Right, thank you.
Clear.
So cladtek was founded in 2003. In fact, we've just had our 20th anniversary, so that's an important milestone for us. We were founded in Australia, as some of you can probably tell from my accent. I'm Australian, and our goal was to become a leader in the mechanically lined pipes, so corrosion-resistant alloy pipelines, and for overlaid products and all the complementary products that go around the pipeline, so plets, plems, slug catchers, pig launchers, etc. All of those components that need to be in CRA. We have 3 manufacturing facilities at the moment. Our original one in Batam in Indonesia, which produces MLP, bends, overlay, and the like. Similar capability in Brazil, but the Brazil facility is more targeted at ultra deep water risers and flow lines, dynamic risers, lazy wave risers, and in Dammam in Saudi Arabia, which again is tailored to that local market. And we're in the process of establishing a facility in Doha in Qatar. This just gives you a general overview. Sorry. Just as a general overview of what we have produced around the world. So you can see we have quite a lot of experience, and we see connectors as the next part of furthering or facilitating the ease and use of CRA pipelines. And we're seeing obviously a big increase in the demand for CRA as it pertains to large gas projects, the rebalancing of the worldwide gas supply, and also with carbon capture. Obviously, if you start re-injecting CO2, that increases corrosion and those sorts of things. So we're seeing quite a big driver there. Anyway, enough of the infomercial about cladtek. So I will now jump to connected pipes. So this presentation, as I said, just gives an overview of the experiences with connectors and where the industry is at the moment, and a little bit about why there's renewed interest in connectors. So first of all, what are connectors and what is this presentation going to focus on? So I think obviously, I guess many of the people on this joining this webinar will be experienced with pipeline connectors. And there's all kinds of connectors. There's bolted connectors like a simple flange. Greylock style connectors. And there's also push fit or MIF connectors, which is another sort of non-reversible way of connecting pipelines together, if you like, a kind of cold welding technology. This presentation is going to focus on connectors that are reversible, so not the push fit style, and connectors that don't rely on bolting. So the various types of connectors that exist, there's the helical thread type or the snap together connectors like Merlin or the GMC connector. There's concentric thread, sorry, that was a concentric thread type. There's helical thread types like you find in OCTG, and these can be adapted for risers and flowline use and have in fact been successfully used. Why is there interest in mechanical connectors? So we see why is there renewed interest? We see there's a lot of interest in increasing use of CRA materials. So that is making the installation of more challenging, more technical requirements on the barge. So the idea of using connectors removes that complexity from the barge and takes it back to a workshop. There's in ultra deep water, people have become very comfortable or in deep water become comfortable with the use of flexible pipes, but in ultra deep water, flexible pipes are proving challenging. So water depths beyond 2,000 meters and in larger diameters. But if your mindset is around flexible pipes, adapting back to a rigid solution is quite challenging in terms of the engineering and work that's required to install a rigid riser and flow line versus flexible. Using connectors makes rigid pipe more like flexibles in terms of deployment. In other words, they're pre-engineered solutions, plug and play. Other area of interest in deeper waters is higher strength materials. So materials that are either difficult to weld or not possible to weld or require post-weld heat treatment. Again, using connectors pushes this activity back into a workshop environment rather than on a vessel. CRA materials fall into that more difficult to weld category. I mean, typically the welding productivity of CRA offshore is around 1/3 that of carbon steel. So that is a big part of the cost difference between carbon steel and CRA materials. There's the additional cost to buy it and the additional cost to install it, and that is offset by avoiding the need to eventually replace it, reduce pigging, reduce chemical requirements. So it's an economic balance. But if a CRA pipe is using connectors, it doesn't know if it's clad or not. So it removes that complexity. And the other area are non-weldable liners or CRA materials, corrosion-resistant materials like titanium or even HDPE. So if you're not having heat in the field, you don't have the issues of damaging the liner through welding. And in the case of titanium, it's not technically possible to clad titanium and carbon steel with a welding process. The only way to attach those two together is explosion bonding, which is not feasible for pipe jointing. Where we're seeing new interest these days is obviously ESG is on everybody's checklist now. What's our environmental footprint? So using connectors allows the possibility to reuse the pipelines and reuse the risers in future, and also aids in the abandonment. So it's a much easier process to reverse the connector process than, say, cut up a pipe or those kind of things. And we're seeing now in ultra deep water where people want to replace flexible risers with rigid because the flexibles can't last a long time. So using connectors enables that to be done in a more incremental way. So what are the concerns with connectors? Well, the main concern with connectors is failure or the light bulbs in series argument, that if one connector fails, then the whole integrity of the pipeline or riser is brought into question. That's of course a valid concern, but there's a lot of data on connectors. and there's a lot of data to support that connectors are extremely reliable and up there with welding, if not better than welding in terms of reliability. The other challenge is that connectors are generally not supported by the major EPC companies because they're welding people. They're not that much interested in developing and promoting a technology that makes every drilling rig and every construction support vessel something that can compete with their sophisticated, deep water J-lay and reeling ships and the like. And connectors tend to be proprietary, and that often interferes with the contracting models of various, particularly state-owned enterprises or state-linked enterprises like the likes of Petrobras, who find, sort of dealing with proprietary items as kind of the last resort solution. And the other challenge is complex and lengthy qualification requirements. Now, that of course is you've got to start the process, but the main benefit of connectors is you can pre-engineer and pre-qualify them for a range of service. So yes, it takes a while to get them qualified in the beginning, but once they are qualified, then it's a plug and play and a copy paste kind of engineering approach. To be used in oil and gas services, what kind of characteristics do connectors need? Typically, we're looking for high pressure capacity and high reliability, resistance to leaking, able to cope with large bending loads, so that's the loads during installation, lateral buckling. In the case of risers, a high fatigue capacity, internal and external corrosion resistance. So the internal resistance, you need the connector needs to be protected from the well fluids that are coming through the pipeline or riser, and externally seawater ingress into the threaded areas or the areas that mechanically lock together is also important for the integrity. So they need internal and external corrosion resistance, and that's mainly achieved by coatings, water resistant seals, so environmental seals, and anodes. Connectors need to be, the easiest way to make people comfortable with connectors is to make sure the connector is stronger than the associated pipe in all load cases. So as long as you're sure that the connector is stronger than the pipe, then the pipe is your limiting factor, and that's what you can go about designing. The issue with that is stress intensification. So the connector can be large and quite stiff, and that can create some intensification factors on the adjacent pipe, but that's not black magic. It's easily, an engineering analysis that can be carried out. Connectors need to be industrially scalable, so easy to manufacture within the existing resources that the industry has. So ideally, a connector should be able to be made in the type of machine shops that you see producing OCTG. There's many of those companies and contractors around, so that provides very quick scalability, and should have characteristics somewhat similar to those in terms of the machining requirements and sealing requirements and the like. It's not necessarily that connectors will be a one size fits all, but of course the fewer connectors that you have to qualify, the better. But we think that the rapid pipe connector is one that can do pretty much every application that requires for flow lines and pipes, at least up to sort of 20-inch. So looking at what kind of connectors have been developed and deployed. So the first ones that I can find that were specifically developed for flow lines or risers, the first one I could find is the FMC differential thread connector. And this connector works by having two different thread pitches. So as the coupling is made up, or as the connector screws together, it pulls together one side quicker than the other. So you back off the coupling, and as you rotate the coupling, you can see as you progress from left to right in that schematic that's also from the early 80s, you can see that the castellations and figures come together and the connector locks up. So this connector was used by FMC, but it's not, they don't promote it anymore. Then Hydril had a connector called the Series 2000, which has been deployed and is still in service on the Magnolia TLP in the export risers. And this is, I think I would say, an improvement or an adaptation of the FMC connector. So instead of using the differential thread, it uses a left and right hand thread. So the coupling rotates rather than the pipe. So you can hold the pipe either in tensioners or slips, and then you can make up simply by turning the coupling rather than having to spin the pipe. So, and that brings it together. And then in this area here, you have some castellation. So these shapes are machined into the end of each pipe. And the idea of these features is when the connector is locked together, then external torque cannot undo the connection. So if the pipe was to say upheaval buckle and lay over on the sea floor, that torque would not be able to undo this connector. So that's obviously a concern that people have with connectors. Also in existing connectors is the Merlin, or what the GMC connector, which is a snap together type connector. So this connector works by having concentric rings that look like threads, but it doesn't actually screw together. It pushes together with some hydraulic pressure that's injected into these injection ports here, which creates an elastic deformation of the pin and the box, and then it's pushed together, and then those things snap back into place. So this connector was originally developed for structural applications, so to connect together the legs of TLP risers, TLP platforms rather, so that the tendons for tension leg platforms, and these days it is being adapted for fluid transport as well. So it has established a market in replacement risers, so seawater risers on old platforms. And the attraction of using this kind of connector in that application is that there is no hot work on the platform when it's replaced. And now this connector is being promoted also for hydrocarbon service. And as far as I know, it has one installed reference in that service. The other kinds of connectors are ones that you'd be quite familiar with, being an adaptation of the OCTG style connectors. So VAM TTR, which is a threaded and coupled connector, which is an adaptation of like VAM top or VAM HC. And there are a number of other OCTG thread technology companies that are promoting traditional threaded type connectors also for riser and flow line use. The concern with these kind of connectors is the possibility of them, unscrewing with external torque, and that they're not really optimized for the purposes of flow lines or risers. They are as they seem. They're an adaptation of something designed for downhole. So our connector, which we will go into more detail, is the rapid pipe connector. And the best way to think about the rapid pipe connector is a BX flange or a BX swivel flange, where we have removed the hub and bolt section that would be here and replaced it with a tensioned collar. But the sealing arrangements and the sealing technology is the same as a BX flange, and the makeup system is which we will show you in more detail in the following presentation, is a tool that grabs the pipe and the connector and pre-tensions that collar, and then you screw in the toothed ferrule. So the pre-tensioning technique is something similar to how you would do a hydrotight bolt tensioning activity. So that's where you stretch the stud bolt and the nuts are turned without load, and then you release the stretch on the bolt and everything is made up. So this is working in the same way, that the collar is preloaded and the toothed ferrule is driven into place without load and locked up, and then the the hydraulic tool lets go of the collar, and then we have a device that measures the residual tension in the collar. So if we compare the different connectors here, and we can share this presentation after. So it seemed to have a bit of background noise there. Apologies. So this matrix here compares the various different connectors, and we have tried to address the various limitations of the existing connectors. And as I say, the differential thread is really not supported anymore. The Series 2000 also, as far as we know, Tenaris is not making it. So the ones that are being promoted in the market these days is the Merlin GMC, the various threaded connectors, and Rapid Pipe. And we think that Rapid Pipe addresses most of the issues that you find with the other kind of connectors. So one of the big challenges of the snap together connector is they're made of very high strength material. So you replace one complicated weld with two welds that are more complicated. And so the sealing area is part of the structural integrity of the connector, which is also a challenge. And Rapid Pipe overcomes most of these. So in terms of developing what the industry needs to adapt these connectors for use with non-weldable liners, we think and CRA liners is very important. So we have that work is ongoing at the moment. More engineering analysis is needed, and a suite of software tools to define how to install connected pipes, what vessels to use, the parameters that you use with different vessels. So like with a drilling rig, on an older rig, you would be able to do a double joint. On a more modern rig, maybe a triple joint. On construction support vessels, quad joints are possible, or if you're going to install using a conventional J-lay or S-lay vessel, in most cases, quad joints should be possible. So all of this needs to be developed and worked out. And if we look back, there's been lots and lots of presentations on connected pipes, and I'd say there's been more studies than there has been risers installed, but there has been quite a few connected flow lines and risers installed over the years, and for the most part, they have been successful. But nonetheless, welding still remains the major technical solution for connecting pipes. So why is that? So this is a statement made 20-something years ago at a presentation. So threaded couplings have been used for many years in the offshore industry, particularly in drilling applications and risers and BOPs and the like, and people are super comfortable with connectors in that application. But as soon as you get to the pipeline or the riser, there seems to be a significant resistance. I mentioned some of the reasons for that before, namely the industry resistance in terms of it's against the industry's, I guess, vested interest in terms of keeping people welding, because all of the installation assets that the main EPCs have are geared around welding. And the industry has relatively high confidence in welded connections. The availability of traditional installation vessels all work around welding. And typically, to date, most of the applications have been medium strength materials that are readily weldable. But now ultra deep water is pushing us in the direction of steels that are stronger and more difficult to weld. CRA also makes these welds difficult to overmatch, which is another reason to be looking at connectors and doing clad welds in a workshop where they can be done carbon steel on the outside for strength and CRA on the inside for corrosion resistance. And that kind of weld is not really practical on a barge. There's also a belief that threaded connectors are more expensive than welding, and that is, there are possibly situations where that is the case, but to use a very good example, so McDermott or Saipem in JLay configuration, so vessels like FDS or FDS2 or Amazon take somewhere between 1.5 and 2 hours to do a fatigue quality CRA weld. And those vessels are $1 to $2 million a day. So if you consider the full cost of those welds, it's, somewhere in the order of 100, more than 50 and less than $100,000. So connectors are relatively cheap. Yes, they take more material than welding, but the time that they save is huge in terms of vessel time. So, we expect that connectors can be made up in around 15 minutes, regardless whether it's CRA or any other kind of complex to weld material, because, as I say, the connector doesn't know if it's clad or not. There has been some instances of connector reliability that's caused, I guess, a negative perception. One of those cases is in Brazil, where Petrobras had a failure, but they literally used a connector designed for downhole in a fairly corrosive surface in seawater, and the connector failed because it got seawater into the threaded area. So it wasn't really a connector designed for the purpose, but nonetheless, people only hear about failure rather than the actual reasons why. But if you look at the installed base for connectors, where they're connectors specifically designed for risers or flow lines, the result is actually very good. If we compare the cost, now this particular table here excludes the cost of the pipe. So we're trying to look here at installation cost, mobilization, and the only material cost that we're adding. So if you can see here, the material line is blank except for the connected one, where we're saying the cost of the material increases by 8.5 million, which is covering the cost of the connectors. And one of the key benefits so this is comparing like a 50 kilometer CRA tieback. You can see that reeling and connectors are not a whole lot different. What we believe would be different in this scenario is if you compared a J-lay vessel doing quads or hex joints with connectors against reeling, because then on a longer tieback like this, comparing a reel ship that has to keep going back to the base versus a J-lay vessel in the field that you can bring the connected quads to the vessel and keep feeding the vessel as it's installing. We don't have the analysis for that yet, but we are working on that. If we compare, however, to a shorter tieback, the difference is really quite stark. And using a drilling rig for the installation, because the rig is already on site. So your mob and demob is almost nothing. It's just a little bit of equipment that needs to go out to the rig to facilitate the installation. And you have your material delta, which again on a short tieback is relatively small. But you can see here that the cost is roughly 75% less than mobilizing and doing it using any of the conventional techniques. So this is just to say where the industry is up to at the moment. So connectors for pipelines do exist. They are qualified and they are already in limited use. There's still further development that needs to be done to address specific sectors of the market, CRA in particular, and other non-weldable liners. But we are seeing increasing interest from operators, particularly those in ultra deep water, to look at connected solutions. Petrobras is one that is running is looking very closely at a connected solution. We know that other super majors that are looking at a conceptual development for 4,000 meter water depth, because drilling now is, I think, the deepest water depth that's been drilled in now is just over 3,600 meters. And of course, if you find something there, you need to figure out how to produce it. And these operators that are drilling in these depths have engaged in studies looking at how that they would go about developing discoveries in water depths up to 4,000 meters. And those conceptual ideas all consider a connected solution which enables the use of high strength materials. Connectors appear to be a very economic, attractive option for tiebacks and very attractive option where CRA materials are involved. And the major obstacle that I can see is mainly inertia. The contracting models, it's not a lack of technology. It's as I say, it's contractual inertia and a mindset. This looking towards the future, why is it different now, and why after 20 years, if there's only been such limited adoption, why do we think that there will be more acceptance and more drive to using connected solutions? So one of those is an explosion in demand of CRA pipes, and that's driven by sort of ultra deep water, high temperature, high pressure discoveries, and also driven by re-injecting CO2. To give Brazil as an example, in the WAG injection lines, the CO2 is going back in the wells, and that of course is creating quite a corrosive environment. So we're seeing more and more CRA, hundreds of kilometers a year rather than 100 kilometers every few years. And we know that the welding productivity of CRA is quite poor, which is why reeling is an attractive option. But we need other options that are attractive as well, and commercial and proven. We expect in the future, as the transition to lower carbon solutions takes place, that there will be more emphasis on tiebacks and using existing infrastructure as much as possible. And again, tiebacks tend to be CRA because they're blood, guts, and feathers back to the processing facilities. I touched on this on the previous page. Deeper and deeper water, looking at the water depths in Namibia and Brazil that are being looked at, say the record depth is just over 3,600 meters. Development solutions are needed. Flexibles are proving not so reliable in ultra deep water. They're also limited on diameter. Collapse strength becomes an issue. CO2 performance has been not as good as hoped. There's obviously work going on with the flexible companies to try and address that. But, in ultra deep water, flexibles are not proving to be a very good solution. And operators and stakeholders want faster development times. Petrobras has come up with their what they call Prod 1000, and their target there is to get production 1,000 days after discovery. Now, if you're in ultra deep water using traditional bespoke engineered rigid riser systems, 1,000 days is extremely challenging, considering all the things that need to be designed and engineered from scratch. Whereas a pre-engineered connected system is, from a deployment point of view, is much more like a flexible pipe, and it is an important part of the aspirations of companies like Petrobras to accelerate cycle times is to have pre-engineered solutions. Let's say I can share this presentation later. All right, so that sort of concludes like the overview of the market, and then the next presentation I will jump to is specifically on the rapid pipe, and my colleague Stephen will help out with this. So Stephen is the inventor of this connector, and we'll go through the attributes of the rapid pipe connector and why we think this is, at least for flow lines and riser applications, the best connector available. So an important point, as I mentioned before, is the best way to think about this connector is a BX flange where we've removed the hub and bolts and replaced it with a tension collar. So it's using, off the shelf and readily achievable dimensional tolerances, cladding solutions for seal areas. All of this stuff, all of the components in that area, or the sealing components, is a very well understood aspect of the connector, and the connector has been designed from the beginning to be used as a fluid transport connector, not as a structural connector being adapted to fluid. So Marine Direct and Stephen invented the connector, and they've been working with NOV and DNV to qualify the connector. And the applications for this connector are, as I was touched on before, it's targeted for flow lines and risers, specifically for it can work. It's very attractive for ultra deep water developments, but it's also attractive for what in the UK they call small pools or marginal field developments, because it enables the pipeline to be reused. So that it is a very important part of the circular economy as we go through more and more tiebacks, and as various jurisdictions at the end of the field life require all of the field infrastructure to be removed. If you can remove it, clean it, inspect it, and reuse it, that is much, much better for your CO2 footprint than if you throw everything, either bury it in landfill or try and deconstruct it and use it and recycle the various components. If you can remove it, inspect and reuse, that is the best way to meet your obligation of removing the infrastructure from an old field and reduce your CO2 impact in the future. It can also be used for plets and plems and structures, can be used for other subsea connections, subsea mining risers. We also are developing applications to use the connector for hydrogen storage, and it could also be used for TLP tethers and caisson installations. So compared to, say, the other, if you say compare this to reeling, the pipe always in the installation modes contemplated for rapid pipe, the pipe would always stay within its elastic range. So unlike reeling, where the pipe has to be able to tolerate high plastic deformations, that is not an issue with a consideration for rapid lay. We expect that quad joints or hex joints will be the most efficient way to install, but this is depending on the vessel capability. There's no requirement for a spool base. This can be done in workshops, can be done in existing facilities. It does not require a dedicated spool base, and could, in certain circumstances, be assembled on a vessel. All of the welding and hot activities that take place in a workshop environment. So in the field, it's a very, very simple installation. So when we use a vessel of opportunity, like a large construction support vessel or a drilling rig, you have one station for makeup and a station for field joint coating. And if you compare that with welding, say CRA, where you have a station for beveling, a station for root and hot pass, NDT of the root and hot pass, potential cutouts or repairs of that for another station, fill and cap, more NDT, more potential cutouts and repairs. You have a lot of, and that's the reason why CRA is relatively low productivity. You imagine all of that just goes away, and you have one station that makes up the connectors. The connector is readily adaptable to CRA materials, readily adaptable to HDPE or non-weldable liners, or liners that can be damaged by heat. That's a key advantage. And the pipe has a smooth bore, and the seal is away from the bore, so protected from erosion and corrosion. Also, in the same way as it is in a BX flange. So it can be used with high strength materials, so welds that can be done in the workshop environment, that need stress relief, things like that, because it's off the critical path of being on the barge. High strength steels are much easier to use. CRA lining, as say non-weldable liners, internal coatings, can work with regularly coated pipe externally. Also in our concept for risers, we can have prefabricated joints of pipe with connectors on one end, pipes without connectors, but are anti-corrosion coated, that in a very short time we can assemble into doubles, triples, or quads, and then using a cast system we can add insulation to the outside. The system's also suitable for pipe-in-pipe type installations. If we compare, what does reuse mean in terms of cost reductions compared to the existing solutions? When we compare it for risers, the installed cost is typically around 50% of the current methodology, and that is not considering the possibility of reusing the pipe. If you do reuse the pipe, looking at a 30-kilometre, 10-inch tieback, the CO2 savings is around 5,000 tonnes per pipeline, so quite significant. Stephen, would you like to talk about the components of the connector?
Yeah, can you hear me okay?
Yes.
Okay, good stuff, Paul. Yeah, thank you for that. So with regard to the, sorry, my daughter was just thinking I'm going to go on to the next presentation, but we're still on the old one. Okay, so we've got the left-hand hub here in green, and that has got, that would be beveled to suit the parent pipe. That's got a series of preloading grooves here. I don't know if you can see my you probably can't see my cursor, can you?
I'm still sharing, so I'd probably need to stop sharing, and you need to start.
Well, if you just move your cursor to suit.
Yep. Can you see that?
Yeah. So the left-hand hub is green, the preloading grooves. On the right-hand side, we have the upper hub in blue, also beveled to suit the parent pipe. On the we have a collar in orange, and that is pre-fitted with the right-hand ferrule in grey. And on the left, back to the left-hand hub in green, that ferrule has a toothed arrangement to allow torquing, but low torque is applied. So we will come to the makeup process a little bit later, but and then of course we've got the BX ring, which is fitted in ring grooves between the upper hub and the lower hub. But these are the principal components. But we have optionally, we have the ability to install secondary seals between the ferrules, both the left and right ferrules, between the ferrules and the collar, and the ferrules and the hubs. We also have a further option of being able to install seals on the upper hub, on the lower hub, if we want to do external pressure tests through a port in the collar. So you can see just either side of that BX ring the slots there for secondary seals. We don't think that's very likely a requirement, but we did use this facility when we were doing external pressure testing during the qualification process. So that's the main components of the connector, and we'll come to the installation, to the makeup process a little bit later. But do you want to go on to the next one, Paul?
Yeah, if I could just add to this configuration here is showing a weld-on connector, But this configuration can also be machined into an upset end pipe to avoid these welds as well. So that's the other option, either having it welded on or not. Yeah. I can go to the next slide.
So shall I carry on, or you carry on,
Yes,
Paul?
so you should be seeing connector qualification now.
Yes, I've got that. Thank you.
Yep, so carry on.
So working with NOV, we were sponsored by Net Zero Technology Centre, who used to be called the Oil and Gas Technology Centre, as part of their plug and play initiative to qualify a 12-inch 5,000 psi connector. So the project included the detailed design of the 12-inch 5,000 psi connector. We manufactured and tested 3 test specimens, which culminated in the issue of the technology certificate by DNV. We did the management of the project, which commenced in May 19, and we completed it in September 22. It took a little bit longer than planned because of COVID, of course, got in the way. But I have to say that NOV did a fantastic job with the detailed design and the qualification. So, of course, we didn't only do a static analysis, we did a fatigue analysis, we did a static testing and fatigue testing. And all the tests worked out very well indeed. Next one, please, Paul. So principal design codes, we designed the connector in accordance with ISO 13628-7, which is the equivalent of the API 17G, also taking account of the DNV STF 101 for pipelines and DNV STF 201 for risers. So we said it's 12-inch and it was designed to suit API 5LX65 pipe of 20.6 mil wall thickness, pressure rating 345 bar or 5,000 psi, with a max operating temperature of 121 degrees, max water depth of 2,000 meters. But it can go way beyond that depth. Next one, please, Paul. So designed to be stronger than the pipe in bending, tension, internal pressure. We also designed it to be stronger in fatigue than a Class D weld. And during the fatigue testing, we saw no signs of damage after disassembly. The next one, please, Paul. So this is some typical FEA finite element analysis outputs. And you can see that how the relative, I'm not exactly sure which load cases these are, but you can, quite interesting to see how the stress distribution looks. The lower one you can see is in bending. Okay, next one, please, Paul. So the connector materials, the hubs made from forging material, ASTM A707 L5 grade 3, with the ring grooves inlaid with Inconel 625. And if necessary, the Inconel can be extended into the hubs for CRA applications. And the CRA would then match up with a CRA liner, which would be slid from the pipe into the hubs and completed with an internal weld. So the collars and the ferrules are manufactured from a much higher, bigger hardness material, but of course they're not welded, so that's of no concern. The 30 this spec of material, 30 CRA. I'm not sure what it's called, but that's the spec. And the BX ring manufactured from Inconel 825. And the threads, quite big threads. They're 2 threads per inch. So specifications, we worked to DNV RP A203, which is DNV's process for qualification of new technology. we, as mentioned before, we worked to API 17G, and yeah, the ISO 13628-7 2005, and the 101, the DNV 101, 201, and very importantly, the DNV fatigue code RPC 203. We also took cognizance of the not listed on here, the API 6A for the temperature and pressure fluctuation criteria. Oh, there it is at the bottom. Yeah. Okay. Next one, please, Paul. So we generated quite a number of documents, which were reviewed and approved by DNV. Well, we had quite a number of comments. You see, we've got the TQRS is listed there. That was the to and fro with DNV. Next one, please, Paul. This is a picture, this is a photograph of the connector fully made up. So this is with the preload already in the connector. So during the makeup process, we would apply about 2,000 tons, and once the connector's made up, we're left with a residual load of approximately 1,500 tons. That additional ring there you can see on the left-hand end of the collar, that is part of the installation device. Yeah, so a completed connector does not have that in place, but that's a nice photograph of showing a very shiny connector before it gets heat treat, subject to sort of temperature and pressure fluctuation activities. Next one, please, Paul. So sample one, a whole range of tests here, which we won't go, as Paul mentioned, we can share this presentation with you later on. A whole range of pressure, temperature. Temperature was on the second later one. But on this one, we use this device down on the right-hand side, down below, to do the tension loading, and we also use the same device to do the low cycle, high stress fatigue loading. Next one, please, Paul. This is sample two, and more internal pressure testing, etc. Sample two was subject to the API 6A testing on temperature and pressure fluctuation, as you can see from the pictures on the right-hand side there. And sample two was also subjected to the high cycle low stress fatigue testing at DNV Singapore. So all the testing was done at NOV Remacut, with the exception of the high cycle low stress fatigue testing, which was done at DNV Singapore. This is the completion of the temperature and pressure fluctuation. And you can see there's a bit of discoloration there caused by the high temperature during the temperature testing. Next one, Pete. So this last specimen had was put onto the bending rig, 4-point bending, and subject to combined tension and bending, etc. And this sample also was sent to DNV in Singapore for further high cycle low stress testing. So next one, please. So this was all culminated in the issue of a statement of qualified technology by DNV, and they were pleased to achieve that. Relatively straightforward process, I have to say, and DNV did an excellent job. Next one, please, Paul. So we think, as Paul sort of touched on earlier, we see not only this being applicable for oil and gas, but also can play its part in the energy transition, where typically we could deploy a pipeline for oil and gas, but it can be pre-purposed for onward recovery, inspection, and reuse for CO2 transportation or for hydrogen transportation. When we say pre-purpose, of course, then we probably more than likely require a CRA liner. So any oil and gas requirement that requires a CRA liner, we should look forward to what type of liner might be required for an H2 transportation project or a CO2 transportation project. So not only saving all the emissions related to new manufacturing new pipelines, but also saving us a substantial amount of cost. Next one, please, Paul. This is your bag, Paul.
Sorry, I was on mute for a second. Yeah, so thanks very much for that, Stephen. So as everyone can see, we're well on the way with having received the type approval from, or qualified certificate of technology from DNV. And as I said, the main target of cladtek for deploying this connector is we believe it's essential to reduce the cost of the installed cost of CRA flow lines and risers. And this particular technology is extremely compatible and beneficial to that goal. Some of the specific benefits that we can get from using this connector is that the triple point, which is the area of great concern typically with a lined pipe, this is where all the interest in fatigue properties is focused. One of the benefits of the connector is we can have that triple point located well up inside the connector where it's thicker and more stable. So we think that using this connector, not only will the connector itself have a very high fatigue rating, but it will enhance the fatigue rating of the MLP as well. So we think it's a very useful technology in that regard. Because CRA clad or lined pipes are designed for life of field, we expect at the end of the service life, providing the anodes and external coating have done their job, that the pipe will be more or less like new at the end of its life. So again, with CRA, it particularly lends itself to being reused. If this technology can be used on carbon steel pipes. We think that the hurdles to compete with welding are more significant comparing carbon steel. But once you jump to CRA, because the welding productivity of CRA is typically around 1/3 of carbon steel, then connectors really come into their own. But the other benefit of being able to reuse, because a carbon steel pipe at the end of its life is going to have used its corrosion allowance, etc. So it's unlikely to be redeployed. Whereas, as I said, a CRA pipe that's been properly designed and installed at the end of life will save for potential erosion from like sand production and things like that. We'd expect it to be fairly close to sort of new condition. So the possibility of reusing is very, very realistic, particularly for things with short field lives. And as I've mentioned several times before, particularly adaptable for non-weldable liners like titanium, HDPE, ultra-high molecular weight polyethylene, that we will see these kinds of, particularly the latter two that we see in seawater injection, also see interest in these kind of liners for mining applications. So deep sea mining where a slurry has to be pulled up through a riser, those sort of wear resistant non-metallics are of interest, and connectors really lend themselves to dealing with those. The other benefit that we can get with connectors, and that we see as a part of this the ecosystem around connected flow lines and risers, I touched on this before, is that it's the drive to reduce the time from discovery to development. And that's one thing that's one area where flexibles are strong, because you have your flexible pipe sitting there, it's got connectors on either end. It's like plugging in the garden hose almost. And we need to get rigid pipe to that sort of ease of use, a plug and play solution. And you not only have, of course, to worry about pressure containment, but you also need to worry about insulation. And then in deep waters and areas with high current, you also need to worry about VIV and drag. We've identified a castable insulation system called GDLX from a company called Bayou. And this particular product is an Exxon product, but the main advantage as we see for the connected solution with this product is it's castable, so it can be put on after. So our concept is we have pipes with liners and connectors, pipes with just liners that are anti-corrosion coated. So those can be sitting in inventory, and when a requirement for the pipe is needed, so we want to install it in the field. So now if you like, we're now in competition with the flexible solution, where the flexible is sitting on a reel somewhere ready to be deployed, and we need to be as close to that as possible. So we can then assemble those components that are already corrosion coated and lined into doubles, triples, or quads that's needed by the installation vessel. And then if insulation is required, as is often the case in ultra deep water, particularly oil requirements, then we can cast that on the outside. Now, another huge benefit of casting the insulation on is it means we can also cast shapes into it. So this particular illustration you see in the bottom left corner is a solution called LGS, or longitudinally grooved strakes. And this has the effect of reducing drag on the riser and also reducing VIV. So you effectively, with casting the insulation on, you get effectively almost free of charge VIV and drag reduction, which are really important considerations in ultra deep water in terms of fatigue life and also field architecture. So like if you can reduce your drag, you can put the risers closer together, because you can't, in a floating system with lots of risers, you don't want the risers banging together. So they need to be separated by a certain amount, and how much they're pulled around by drag is really important. So if you can reduce the drag, you can put your risers closer together, and that also reduces the overall loads on the system. And that brings us up to question time.
Did you want to do something on insulation, Paul?
Yes, sorry.
Oh.
Was that in?
No, I've got it.
You've got it?
Okay, if they have
I've got it.
if they have a question, they can either try to speak up or write in the chat box. Thank you.
Yeah. Okay.
We're just going to show one video showing the installation. So you're going to do that, Stephen, or do you want me to
do that?
I'll stop sharing.
Okay. Right, I'm start sharing now. And this one here. What do I do? Am I sharing this now?
Yep, we're seeing your screen.
Okay, good. To click on slideshow from the beginning. Okay. So that was a reminder of the connector configuration. So in terms of installation kits, there's various options. We're considering possibly a new build SLA system, an upgrade to an existing SLA system, a new build JLA system, or an upgrade to an existing JLA system. And it depends what's available, who's interested in working with us, etc. This is an envisaged new build SLA system, more for shallow water applications. And as you can see with the configuration, there's no need for the internal line-up clamps, no need for welding stations. The makeup tool can be integrated into the the overall makeup station. We can use the standard tensioner from Remacut, part of NOV, that can take the can pass the made-up connector. The stinger rollers can be designed to suit the passage of a rapid pipe connector. Can be installed on a vessel of opportunity, and fully automated, significantly reducing the number of people on board. This is an envisaged S-lay system, and this is a little video attached to this. And I'll just run it now.
Yep.
So you can see the preloading going on, the color translation, the preloading, and then the wind up of the ferrule, and then it passes through to a station where we can coat the connector with whatever type of coating is required. Normally would be a shrink wrap type of coating. Moving on. Done that one. So this is we're tight on time now. So this is the overall sequence for doing the fabrication of the doubles or quad joints on shore. And then we have the option of the secondary seals, as discussed earlier. We have the option of coating the components if required, and we have the option of installing the CRA internal liners onshore. This is running through the mobilization of the equipment, either in S-lay or J-lay. We won't go into too much detail there, but we've just given you an overview there of typical S-lay setup or a J-lay setup. And we also run through the typical pipe lay procedure. And you'll once we send you the presentation, that can be read through in a bit of detail. But it's very similar to what is carried out with welded pipelines or risers. That is continuation of the procedure. This is how a typical connector makeup device would look on board an S-lay vessel or a J-lay vessel. And I'll put the laser on here. This is the collar, and you can see on the right hand side here the grooves in the lower hub where the preloading is applied, and you can also see the grooves on the right hand side of the collar there, and you can see the rams that would be preloading that collar. And this right hand ferrule in red here, this would be the one that would be have the cog arrangement, and there would be a cog type setup in this part of the device here to apply a low torque to that ferrule. Moving on. So this is the process with a bit more detail here. So the collar is pulled back. You've got a pre-installed ring here, BX ring. You've got the ferrule on the left-hand side here. You've got the collar and a pre-installed ferrule on the right-hand side. You bring the two hub faces together like that. Then the collar is slid over. And then the preloading tool, which is not shown here, engages with these preloading grooves on the lower hub and the preloading grooves on the collar. And the left-hand ferrule is screwed into the collar, and then the tooling's removed, and you've got on a 12-inch 5,000 psi, you've got typically 1,500 tons of residual load locked into that collar. And for joint integrity, of course, very important. There's a number of things we would monitor. Of course, there's the manufacturing, which has to be carefully controlled. Protection measures during loadout and installation. Close visual monitoring during makeup. Pre-calibration of the preloading device. Monitoring and measurement during the makeup of hydraulic pressure, load displacement, residual strain in the collar. And we envisage a contactless strain measurement device that will measure precisely how much residual strain there is in the collar following makeup. And if you know the residual strain, you know the residual load in the connector. And because we got the potential for reuse, we see matching up with digital twin technology to be particularly applicable to this technology. Outline procedure continued. Again, I won't go into detail here because we're very tight on time now. And that's the end of this part of the presentation.
So, are there any questions from anybody?
Okay, maybe our audience, maybe if they have a question, they can either try to speak up or write in the chat box. We have a question from Shema. Okay, Mr. Bull, Mr. Steven. Okay. We have a question in the chat box.
I'm not able to see the chat box. Where do we open? Is that in notes or?
Yeah, Shema say, did you perform any sour testing in the material?
Yeah, it's designed for in accordance with the NACE requirements for general kind of oil and gas applications, but we haven't designed it for kind of exceptional sour service or in terms of the testing that we did for samples 1, 2, and 3. So if we were going for absolute sour service, we would need to do some additional testing. But of course, a lot of it comes into the material selection. So I would imagine sour service, Paul, you could probably comment more on that.
Yeah, I mean, yeah, as I say, it's more of a material selection question, and yeah, we can make the components sour service, and also so our main target here is CRA materials. So from an internal point of view, you know, the carbon steel components are protected by the CRA layer.
Okay. And also said, does the connector work with concrete coated pipe?
Yes.
Yes. 2 yeses.
Okay. Okay. Any questions from audience? Okay. Everybody know I'm thankful. Thank you, Mr. Poole, and thank you, Mr. Stephen. It was quite informative and intense. Although thanks for audience everywhere worldwide, I think it delivers a good value for schedules. I think it will have it spread more widely in the coming years. So thank you very much for your time. Really appreciate it, and hopefully you join our community. And also I have another sessions in the future.
Okay, well, and thank you so much for the opportunity, and we'll look forward to seeing you in Egypt sometime.
That's so nice.
And Mubarak Kareem.
Yeah, many thanks. Many thanks for organising, and many thanks to Ahmed from our end for organising. Was Ahmed on the call, or was it a bit late for him? I wasn't sure.
I think he was there.
Oh, yeah.
I'm in.
All right, you're there. Okay. Well, many thanks, Ahmed, for doing all the arrangements with the Egyptian Subsea Society.
Thank
Yeah,
you.
yeah, for sure. Yeah, we are waiting for you in Egypt. Thank you.